as a continuous time Fourier transform. So let's consider an aperiodic xn, which is non-zero from minus n1 to n2. This is x of n. And I periodically extend it. Uh, n. So from here to here, it's periodic extension. Periodic extension of x of n, and this gives me x tilde n. And obviously from x tilde n to x naught, we know if we make the time period go to infinity, the periodic signal becomes an aperiodic signal. Okay, so let me try this thing. If I get this one, copy. Wait. Copy. Copy. Paste. Okay. Here. Paste. Somewhere here. Paste. Somewhere here. Okay, good. Let me erase this one, and draw this one again. This is n. Okay, so there is some n over here. So this is n minus n1. This is n plus n2. This is minus n minus, this minus n. Oh, sorry. This is minus n minus n1. This is minus n plus n2. So basically we have, this is the original one, and these are periodic extensions. These are periodic extensions. Okay. Okay. From discrete time Fourier series, we know x tilde of n equals k equals some n points a k e j k 2 pi by n. This, by the way, is omega naught. And then a k's are 1 by n points again, x tilde n e minus j k 2 pi by n. Both are periodic and discrete. Okay, x tilde of n equals x n over one period that includes minus n1, that includes minus n1 less than n less than n2, and this is this one. Okay, this implies ak equals 1 over n n is equal to minus n1 to plus n2 x of n e minus jk 2 pi by n which is equal to, now x of n, this x of n is non-zero from minus n1 to n2. So obviously, whether I change the limits from minus infinity to plus infinity, the only non-zero portion is what that matters. So what I'm going to do here is I'm going to say this is equal to 1 over n. N goes from minus infinity to plus infinity, x of n e minus j k 2 pi by n. And I have not used an x tilde of n over here. Why? Because x tilde of n is equal to x of n over minus n1 to n2. Okay. Let me define x of e j omega, just like we defined x of j omega, as n is equal to minus infinity to plus infinity, x of n e minus j omega n. The fundamental difference between this one, the fundamental difference between x j omega and x of ej omega is, and what is that fundamental difference, where we know x of j omega is minus infinity to infinity x of t e minus j omega t dt. This one is periodic. This one is periodic. Why? Because if I replace omega, so replace omega by omega plus 2 pi, then x of ej omega plus 2 pi equals x of ej omega, because e minus j 2 pi n equals 1. So this is the fundamental difference between x of j omega and x of j omega is, okay, this one is periodic. Let me write it again. This is periodic. Okay. AKs are also periodic. So if AKs are periodic, I can write AK equals 1 over n x. 1 over n x. This is omega here, and there is omega over here. This is AK is 1 over n. 1 over n. This is x of n, and this term is k omega naught. So I'll write 1 over n x e j k omega naught, where omega naught is 2 pi by n, and x tilde of n equals 1 over n summation n values of small k, ak, which is x of ejk omega naught, into ejk omega naught n. However, 2 pi by n is equal to omega naught. This implies 1 over n equals omega naught over 2 pi. If I substitute this value in here, this implies x tilde of n equals 1 over 2 pi k x ejk omega naught ejk omega naught n. Let me sketch this figure now. This is omega, and this x of ej omega, by the way, is continuous. This is a continuous function of omega. This is a continuous function of omega. Of omega. So periodic continuous function of omega. So let me draw it here. So we have let's say this is minus pi, this is plus pi, this is 0, and this is x of ej omega into ej omega n. This point is k omega naught, and just like before, we find this area. This point is k plus 1 omega naught, and this area is this width. This width is omega naught. This width is omega naught, and this height is x of ejk omega naught, ejk omega naught into ejk omega naught n into omega naught. This is the area of this one, which is exactly this thing. Oh, sorry. There is a omega naught over here too. There's an omega naught here too. So this is simply the area. So again, we are summing the area. We are summing the area under this curve. So as n tends to infinity, omega naught goes to d omega. Omega naught goes to d omega, and x tilde of n becomes x of n, right? This is periodic. This is aperiodic. There are n of these, so also summation as in the summation. This summation is over n values. This summation is over n values. Each width of omega naught is 2 pi by n. So n times 2 pi by n implies the integral is going to be over 2 pi. So this is the fundamental difference between the continuous time, the Fourier transform of a continuous time aperiodic signal, and the Fourier transform of the inverse Fourier transform of an aperiodic signal, and the inverse Fourier transform of an aperiodic signal for discrete and continuous time. That the integral for this case is going to be over 2 pi. Why? Because this one is periodic. This is periodic over 2 pi. So this implies x of n. So this x of tilde n becomes x of n. 1 over 2 pi is 1 over 2 pi. 1 over 2 pi integral. So in taking n terms, each of width 2 pi by n, take n of these. So obviously the total width is going to be 2 pi. So we say the integral is over 2 pi. So integral over 2 pi period x of ej omega n d omega, right? Okay, good. This by the way called the inverse Fourier transform, and this is the synthesis equation. This is the synthesis equation, and its counterpart is x of each omega, which we already defined is n is equal to minus infinity to plus infinity, x of n e minus j omega n, and this is the Fourier transform, and this is the analysis equation. Okay. This is periodic. And low frequency signals. For low frequency signals, the spectrum is concentrated around even multiples of 2 pi, which means low frequency signal is going to be like this. It's going to be periodic. So this is omega naught. No, this is, let's say this is 0. This is 2 pi. This is minus 2 pi, and so on and so forth. This is x of ej omega. And high frequency signals, spectrum is concentrated around, so this is even, so that is odd, around odd multiples. Actually, this should be even multiples of pi. Even multiples of pi should be all right. Around odd multiples of pi. Okay, which means actually I could just bring this over here. This is pi, this is 3 pi, this is minus, this is pi plus 3 pi, and this is minus pi, okay? Pi minus 3 pi, and this is again x of ej omega, okay? What about convergence issues? If we look at x tilde of n, this x tilde of n is over 2 pi. Since this is over 2 pi, this is not over minus infinity to plus infinity. So there are no convergence issues associated with x of n. No, there are no convergence issues. There are no convergence issues associated with x of n, since the integral is over finite interval. The integral is over a finite interval, and the finite interval is 2 pi. X of ej omega converges when x of n is absolutely summable. This implies x of n absolute is less than infinity, but this implies this is square. This is square summable. This is square summable. This, by the way, simply means this has finite energy. Finite energy. So all finite energy discrete time aperiodic signals have a discrete time Fourier transform. So this implies all finite energy discrete time aperiodic signals aperiodic signals have a discrete time Fourier transform. Let's do some examples. Let's do some examples of the continuous time find some Fourier transform of discrete time aperiodic signals. So the first one, just like for the continuous time case, x of n is a n u n. U n is same unit step, and we assume a is less than 1. So x of ej omega is n is equal to minus infinity to plus infinity x of n e minus j omega n, which is equal to, because of this u of n, this lower limit is going to be 0. N is equal to 0 to infinity a e minus j omega whole n. This is the geometric series, and this gives us 1 over 1 minus a e minus j omega, which is equal to, so this is x of ej omega. Obviously, x of ej omega is complex. This is complex, so has a magnitude and a phase component. So what is the magnitude component? So let me write this one as 1 over 1 minus a cosine of omega minus plus j a sine of omega, where I've used Euler's identity. So Euler's identity, and Euler's identity says E minus j omega is cosine of omega minus j sine of omega. So this minus with this minus becomes a plus j. And what is the magnitude? So x of ej omega magnitude is simply 1 over this square plus this square under root, square root. So this whole square is 1 minus a whole square is going to be 1 square plus a square cosine of omega square plus a square sine square plus a square, and the cross product here is minus 2a cosine of omega. If I plot this magnitude, obviously we need to know, we need to be careful that all these Fourier transforms are periodic. So if I plot this magnitude when a is between, when 0 is less than a is less than 1. So when 0 is less than a is less than 1, at omega is equal to 0, this is 1. So this is 1 plus a square minus 2a, which is 1 minus a whole square, cancels with this one, and we are left with 1 minus up. Since a is, so this is, so at omega is equal to 0, this is 1 plus a square minus 2a, which is equal to 1 minus a whole square. Since a is between 0 and 1, 1 minus a is positive, and 1 over 1 minus a is going, 1 minus a is a small number, 1 over 1 minus a is going to be large, and this function goes like this. So I'm only going to sketch from minus pi to pi because it's going to repeat. Okay, and this point is 1 over 1 minus a. What happens at pi? At omega is equal to pi, this becomes minus 1, so this becomes 1 plus a square plus 2a, which is equal to 1 plus a whole square. This is a 1. 1 plus a whole square. 1 plus a whole square is greater than 1, so this point is 1 over 1 plus a. Okay. And this is obviously a low pass signal. This is a low pass filter. What about if A is between -1 and 0? So if A is between -1 and 0, again the magnitude, this is the magnitude, 0, magnitude here. So if A is between -1 and 0, at omega is equal to 0, again, this is going to be 1 minus A whole square. But since A is negative, 1 minus A is going to be greater than 1. So if it's greater than 1, this is going to be less. And this is going to go like this. And why here? Because at pi, this is going to be 1 plus A whole square, but A is negative. So this one is small. This one's small, 1 over 1 plus A. So this is large. So this is minus A, this is 1 over 1 minus A, and this point is 1 over 1 plus A. And this is obviously, and the frequency, this is periodic, so obviously there is something over here. There's something over here. So obviously frequencies are concentrated around pi, so this is a high pass filter. Okay. And similarly, this one is actually going like this. This is going like this. So this is a low pass filter. So we have, this is low pass filter. Why? Because frequencies are concentrated around 0. So we are not going to, I'm not going to sketch for minus infinity to plus infinity. You can always periodically extend it. Okay, let's look another one. Example. X of n is equal to A absolute n. This is exactly the same example as that we did for the continuous time Fourier transform, where we had E minus A absolute of t. Again, A is between plus minus 1. X of ej omega is now actually there are two sums. One goes from n is equal to minus infinity to minus 1. This is A minus n, E minus j omega n, because when n is negative, over here, when n is negative, this term is positive, this is always positive, plus n is equal to 0 to infinity A n E minus j omega n. This one is easier. This is simply 1 n is equal to 0 to infinity A e minus j omega whole n. And we know this geometric series. For this one, let's assume let p equals minus n minus 1. If p equals minus n minus 1, so when n is equal to minus 1, this is plus 1 minus 1, so p is equal to 0. When n is equal to minus infinity, this is plus infinity, and minus n is equal to p plus 1. If minus n is equal to p plus 1, so this is A e minus j omega, or A e plus j omega into minus n. So instead of this minus n, so this term is A e plus j omega raised by minus n. But since minus n is equal to p plus 1, I'll change this one. I'll put this p and I'll bring the one term outside. Right? So this is A e j omega p plus 1. I can bring this one out because this is independent of p. So this is, again, both are the same now. So this is A e j omega, both are geometric series, over 1 minus A e j omega. And this is plus 1 over 1 minus A e minus j omega. This one is a conjugate. This is a conjugate of this one. So obviously, when we have conjugates being multiplied, so this will become 1 into 1 is 1, minus A e j omega into minus A e j omega is minus 1 is plus A square minus A common, and this is e j omega plus E minus j omega, e j omega plus E minus j omega. But what is e j omega plus E minus j omega? This is simply 2 cosine of omega. And in the numerator, I have A e j omega into 1. This is A e j omega minus A square, E minus j omega, E plus j omega goes away, plus 1 minus A e j omega. So this cancels with this one, and I'm left with So x of ej omega is simply 1 minus a square divided by 1 plus a square minus 2a cosine of omega. So the denominator is exactly the same. The only in the numerator, instead of 1, we have 1 minus a square. If you go home and plot, you'll get exactly the same plots as for the previous example. And for 0 less than a less than 1, this is a low pass filter because the denominator is the same. And for minus 1 less than a less than 0, this is a high pass filter. Same magnitude plots as the previous example. Okay. What about a square pulse? So let's say I have one here. This is 1. This is 0. This is minus 1. This is plus n1. This is 0. This is 0. This is omega. I'm sorry, this is n. This is n. And this is x of n. So this kind of a square pulse. This is a kind of a gate function. So x of ej omega. So x of ej omega is n is equal to minus n1 to plus n1 because it's 0 outside, minus n1, n1. This is 1 e minus j omega n. So again, I do the same trick. I say let n plus n1 because I only know the summation for the geometric trees when the lower limit is 0. So I want to make the lower limit 0. So let n plus n1 equal some p. So this equals. So when n is equal to minus n1 plus n1, p is equal to 0. And this was 2n1. And this is e minus j omega. And n is equal to p minus n1. So e minus j omega p here. And e plus j omega n1 I'll take outside. E plus j omega n1 I take outside. Right? So this minus plus. So this becomes e j omega n1 into 1 minus e minus j omega. So maybe I write it like this. So p goes from 0 to 2n. So this is 2n1 plus 1. Maybe I write it here. Let me write it down in the next line. So this is equal to e j omega n1, 1 minus this argument into upper limit plus 1 divided by 1 minus this argument e minus j omega. The trick to solving this one is I remove this 2 from here, put a half here, and bring this 2 outside, right? It's one and the same thing. So let me write it neatly. So this is n1 plus half into 2. And this I can also write as e j omega 2 e minus j omega by 2. So this one is the phase function e j omega n1. Bring half the angle outside. Which is e minus j omega 2. So e minus j omega by 2. Obviously, this is e plus j omega by 2. This is minus e minus j omega by 2 because e plus j into e minus j is 1. And do the same trick here. Bring half the angle outside. So bring e minus j omega n1 plus half outside. So inside you'll be left with e plus j omega n1 plus half minus e minus j omega n1 plus half. So plus j omega n1 plus half minus j omega will give you 1. Minus j omega n1 plus half minus j omega n1 plus half is going to give you this times 2 times. This thing by Euler's S sine, this thing again by Euler's S sine. So this one is sine omega n1 plus half over sine omega by 2. What about this term? So for this term, let's look at the exponents. So we have n1, we have minus n1, we have minus half. Everything has omegas in it. And this is minus half, goes in the numerator, is plus half. So this cancels, this cancels, this cancels, this cancels. There is no phase. There is no phase. Why? Because this function is symmetric around 0. If this was shifted, then there would be a phase. But since this is not shifted, there is no phase. So this function, so this implies x of ej omega is equal to this one. This is a periodic function. This is periodic. This is periodic. And this is the discrete time counterpart. Discrete time counterpart. Maybe I write it again. This is the discrete time counterpart of sync, which was aperiodic. This was aperiodic. And let me sketch it for you. Sine 0, undefined. So this will have value n1, 2n1 plus 1 over 2 divided by half. So this value is 2n1 plus 1. And this function is like this. I have drawn this one. This is x of ej omega. I have drawn this for n1 is equal to 2. This is pi. This is minus pi. This is omega. And this is 0 at nulls at omega into 2n1 plus 1 over 2 equals n pi, because sine of n pi is 0. Sine of n pi is equal to 0, or omega is equal to 2n pi over 2n1 plus 1. So for our case, this is actually 2 pi over 5. This is 2 pi over 5. This is 4 pi over 5. This is minus 2 pi over 5. This is minus 4 pi over 5. And this is periodic. All x ej omegas are periodic. Okay. So for the continuous time Fourier transform, we also said, can we find the discrete time Fourier transform for periodic signals? So let's see whether we can do it for the discrete time case too. So Fourier transform of periodic signals. Let x of n equals ej omega naught n. If x of n is equal to ej omega naught n, what is the Fourier transform? Our Fourier transform is going to be x of ej omega. For the continuous time Fourier transform, this was ej omega naught t. The Fourier transform, recall, ej omega t, the Fourier transform was 2 pi delta of omega minus omega naught. But this one is periodic. This is periodic, so this will be 2 pi delta of omega minus omega naught minus 2 pi L, where L goes from minus infinity to plus infinity. Let's check. x of n is 1 over 2 pi integrate 2 pi e x of ej omega x of ej omega into ej omega n d omega. Okay, let me sketch this one. This sketch is like this. You have omega naught 2 pi, then you have omega naught plus 2 pi, omega naught minus 2 pi, and this goes on. This goes on here. This is omega. This is the sketch here. So this is x of ej omega. Okay, so let me integrate this one. So 1 over 2 pi. Let me integrate this one from minus pi to pi. So this is some minus pi, this is some plus pi. So I integrate from minus pi to plus pi summation L 2 pi delta omega minus omega naught minus 2 pi L into ej omega n d omega. There is only one impulse, at omega naught within 2 pi interval. So this implies this is equal to this 2 pi cancels by the way with this 2 pi. So I'm left with, so if I apply the shifting theorem, if I apply the shifting theorem, this integral is going to be equal to the value of the delta function at where the delta function occurs. So this is ej equal to the value of the exponential where the delta function occurs. So this is ej omega naught n. Okay, so ej omega naught n has a Fourier transform to summation 2 pi summation L goes from minus infinity to plus infinity delta omega minus omega naught minus 2 pi. So this is periodic. So compared to ej omega naught t, where there was only one impulse at omega is equal to omega naught, this is a series of pulses from plus minus for omega naught plus minus 2 pi L. Okay. Now consider a periodic. So obviously if this was k omega naught, so this omega naught will change over here. Okay. So now consider a periodic xn with period n and discrete time Fourier series representation x of n is k over some n values ak ej k ejk 2 pi by n into n, or x of ej omega is simply k is equal to minus infinity to plus infinity 2 pi ak delta of omega minus 2 pi by n k, and this one is because of periodicity of AK. Because of the periodicity of AK. Let me do some example and then I'll come back to this one. x of n is cosine of omega naught n, where say omega naught is 2 pi by 5. This is equal to half e j omega naught n plus half e minus j omega naught n, and x of e j omega is simply summation. 2 pi will cancel with this 2, so we have, or maybe let me write it, half 2 pi delta omega minus omega naught minus 2 pi L plus half L 2 pi delta, this is omega naught plus omega naught minus 2 pi L, or 2 cancels with this one, 2 cancels with this one, and I'm left with, this implies x of ej omega is equal to pi L delta omega minus 2 pi by 5 minus 2 pi L plus pi delta omega plus 2 pi by 5 minus 2 pi L. If I sketch this one, the sketch is going to look like this. So I have omega is equal to at plus 2 pi by 5 minus 2 pi by 5. So this is 0. 2 pi by 5 minus 2 pi by 5. This is pi. And then I have this one at plus 2 pi and minus 2 pi. So this is 2 pi. So 2 pi plus 2 pi by 5. And this is 2 pi minus 2 pi by 5, and this is 0 here, this is 0 here, and then at minus 2 pi, again I have this impulse, and I have this impulse, again this is pi. This point is minus 2 pi plus 2 pi by 5, and this point is minus 2 pi minus 2 pi by 5. So this one, for the discrete time, for the continuous time Fourier transform, we would only have this one, but now these impulses are also periodically repeated at plus minus 2 pi and so on and so forth. This is x of ej omega. Okay. One more. X of n is summation k delta of n minus kn. So this is like this. So you have impulse here, impulse here, impulse here. This is all 1, 0, n minus n. This is continuous here, continuous here. This is n, this is x of n. We know the Fourier series is 1 over n. Fourier series is 1 over n. N is equal to n, x of n, e minus j, k 2 pi by n, n, and this is simply 1 by n, just like it was 1 by t, and this is for 0 less than k less than equal to n minus 1. Don't forget that this is periodic. Okay. And what about x of ej omega? X of ej omega is simply 2 pi ak over here. This is 2 pi ak. So 2 pi n k equals minus infinity to plus infinity, and then delta of omega minus 2 pi by n k, which is exactly the same as for the continuous time Fourier transform, except no, it's exactly the same as for the continuous time Fourier transform. This is 0, this is n, this is 2 pi by n, this is 2 pi by n, this is minus 2 pi by n, this is 2 pi by n, this is periodic, this is periodic, this is omega. Okay. Okay, so let me go back to the for the general for a general periodic xn, for a general periodic xn, obviously discrete time, x of n is k is equal to 0 to n minus 1. So I'm taking any n samples, ak ej k 2 pi by n into n, which is equal to a0 plus a1 ej 2 pi by n into n plus, this k is 1 here, k is 0 here, plus a2 ej 2 pi by n 2n plus so on, plus a n minus 1 ej 2 pi by n into n minus 1 into n. Okay, good. At omega not, at omega is equal to 0, what do I have? At omega is equal to 0, I have two pi a0, and since a's are periodic, so there will be a 2 pi an, because ak is equal to ak plus rn, if you recall. So recall ak is equal to ak plus rn. So a0 is equal to an, and obviously so this is at 0, this is at 2 pi, this is omega, and this is minus 2 pi. This is 2 pi a of minus n. Right? Okay. So this corresponds to a0. Maybe I write this corresponds to a0. So for a0, what happens for a1? What happens for a1? Let me do this thing. If this works, let's see. Copy, paste. Okay. So this one is shifted by how much? This one shifted by how much? This one now becomes 2 pi. This one becomes 2 pi by n. This becomes 2 pi plus 2 pi by n. This becomes minus 2 pi plus 2 pi by n. This for a1. This one becomes a1. This becomes an plus 1. This becomes a minus n plus 1. Right? Right? So this is shifted. What about a of n minus 1? Again, for a of n minus 1, let me see. Copy and paste. So this one is going to be shifted. This is going to be shifted by, this is going to be shifted if an minus 1. So an minus 1 is probably going to be here, right? Here. Okay. So this becomes this is an minus 1. So this is exactly less than this 2 pi, right? So this is 2 pi minus 2 pi by n, because if you do that, this will be equal to 2 pi over n into n minus 1. Okay, and this one would be at minus 2 pi. This one would be at minus 2 pi plus 2 pi over n into n minus 1. Oh, sorry, let me change this one. This is minus n minus 1 minus n minus 1, and this is n minus, this is n minus 1, right? Let me write this one again. Minus n minus 1. Right? So this one is 2 pi minus 2 pi. So this is 2 pi comes out, 2 pi over n comes out, and I am left with this is n here and n minus 1. Right, this is all right. And this one should be 2 pi plus 2 pi by n, and this one should be 2 pi minus 2 pi plus 2 pi by n. So if you look at them, these ones and probably this one, maybe, wait. So if I connect them, so there's a one over here. So if I reconstruct them, there will be a bunch here. This is from 0 to n minus 1, then n to 2n minus 1, and then I'll have minus 1, 2. So this is omega. This is x of ej omega for a periodic signal. And this would be minus, this would be minus n minus n minus n, right? So minus n plus 1, minus n plus 1. So n minus 1 to 0. So these are n values, these are n values, and these are also n values, right? Minus 1 to minus n, these are n values. Good. So we have 2 pi a0 over here, 2 pi a0 here, and we also have 2 pi a0 over here, 2 pi a n, and we also have 2 pi a minus n. We also have 2 pi a minus n. At 1, I have 2 pi a1. This is at 1, and then at 2 pi of 2 pi of n and 2 pi plus 2 pi n. So this is again 2 pi a of n plus 1. And obviously over here I have 2 pi of a minus n plus 1. And then goes on. For n minus 1, I have 2 pi a n minus 1, 2 pi a n minus 1. And this is repeated over here. This is repeated over, which is 2 pi a minus n minus 1, a minus n minus 1. And this is also repeated over here. This is 2 pi. What is this one? Oh, no, this is 2n minus 1. 2 pi of a into 2n minus 1, right? So we have this signal. This is repeated. Spectrum is repeated over here, and the spectrum is repeated over here. This was not the case for the continuous time Fourier transform, where continuous time Fourier transform was aperiodic. So let's stop here. Next time we'll do the properties of discrete time Fourier transform and applications, probably in that lecture, in the lecture that follows it. Okay, thank you.